All okay? Okay, so I'm Drone. I didn't get to do an introduction earlier, but I love music. Like I've been playing piano for 12 years. I've been playing the sax for 5 years. And I really love music composition. And it turns out so does AI. AI also really loves music composition. So I've been looking into actual ways that AI generates music. So a lot of people think that, oh, artificial intelligence can't be applied in music because music is like art. You can't teach an algorithm to make music. It wouldn't have that soul. It wouldn't have that human factor. But Magenta thinks differently. So Magenta is a subset of Google Brain, and they're essentially a project that's like working on making music and art using machine learning and teaching algorithms to make these things. So let's look at a quick example.
Joan, we can't hear anything. Maybe it's because your headphones are in, so you might have to like unplug your headphones.
Uh, so I'm gonna stop there, but the really cool thing about it is that that's entirely algorithmically generated. Like there is no human input there. The algorithm just generated that all on its own with a bunch of training on human examples, but that entire piece with structure, with form, with different motifs that it developed, with different harmony and different melodies, and it did it entirely on its own. So now let's think of, I'm sure you've heard of this, the Berlin Philharmonic. They do like virtual concerts for across the world. And they've been stepping up now in this like pandemic situation where a lot of people are stuck at home. But what if we replace them? So if AI can make the music and generate these long-term structures of songs and stories that actually like convey a message, and they can also perform that more accurately and better than human musicians can ever do, then why have the humans in the loop at all? So this is essentially what this is where I think AI music is going. But Magenta didn't get there overnight, right? They've gone through a lot of evolution throughout their whole like lifetime as an organization. So I want to take you through that and actually show you how they built what they did. So I think the first key thing is how we represent music as data. So this is how this sound clip sounds like. So essentially each of these notes is given a certain pitch number, and it's given a start, end time, and velocity. Velocity is essentially the volume at which it's played. So like this one, here they're all the same, but you might have varying levels of dynamics to show this area is loud, this area is soft. And then once you do that, use a structure called a recurrent neural network. So essentially what a recurrent neural network does is it deals with sequential data. So music is in time steps, right? You have time step 1, time step 2, and so on. And then you have notes at each of them. So basically what you do is that you put these neural networks in a loop, and each of these cells is going to predict a note, and then it's going to pass that note to the next one, and it's also going to produce this hidden state. And this hidden state essentially is like this cell over here can use this hidden state and essentially say, oh, that's what happened before, so I'll use that information in making my next prediction. So these RNNs are basically looping in on themselves so that they can actually take information from the past and use it in the present. So each of these cells are have something called a neural network. And it's not super important how they actually work, but the idea is that you have your data, your input here, and these are all numbers, and then you apply some sort of function to them, whether it doesn't really matter what it is, but you apply a function and then that transfers to the next neuron. So basically each of these lines are individual weights, individual functions that can be tuned, and then you get your output. So this would be your like classification. And essentially you take your data, you pass it through the network, and then you say, okay, how wrong was the neural network? And then you just pass that back through, and then you tune all these individual lines, and eventually you get a neural network that actually does what you want it to do, that it gives a correct classification. So what a basic recurrent neural network will do is that each of these is like a neural net, and then it'll pass the hidden state, and this is the input. So it'll just pass that data along the chain, right? But the issue is that here, as you can see that here there's only 3 cells, but there might be hundreds of cells. So something that was like, for example, in text, right? If you wanted to keep information from like the beginning of the paragraph, that's really hard to do. It's like a game of broken telephone. Each time you pass a piece of data, it's going to lose a little bit of its information. And the problem is that what happens is the RNN actually loses context. So what we do, we use a structure called an LSTM, or a long short-term memory network. And basically this line going through right over there, what that's doing, it's like acting as the working memory. So like it'll keep, oh, this is sort of like, oh, I'm holding, who is the subject in this sentence, or what is this paragraph talking about? And then it'll basically hold that over so that more information can be transferred over longer periods of time. So it can actually remember, hey, this is what happened at the beginning of the paragraph. So this is what I should predict next. But the issue is, hang on, I have to move the Zoom thing. Here's what it actually generates. So that's not very impressive. And no way is it even comparable to the Berlin Philharmonic, right? So for that, we need to level up. We need to enhance these RNN structures. And the way we do that is we give them 2 main level uppers, I guess. We have the look back function, and this essentially allows the RNN to actually go back in time and look at what happened in the past in more detail. So if we think about words and sentences, essentially what a look back will do, it'll say, okay, how did we start the last sentence? So if it's at the beginning of a sentence, we'll pass in the information of what happened last sentence with a stronger bias. So it'll essentially think, oh, this is what happened last time we started the sentence. And this is super helpful in music because music has these type of repetitions, these type of patterns from one measure to the next, one bar to the next, and one section to the next. So look back is super helpful. And then we can actually evolve that further to create attention. And attention is essentially saying, oh, this is what we should care about. This is what is valuable to the neural network in the future. And this attention mechanism allows it to say, okay, I'm going to remember this pattern and I'm going to use it much later. And that allows it to create more interesting melodies that are more human and less just playing the same note over and over again and just wandering off into nowhere. But again, it's still only generating one note at a time. And it doesn't sound anything like a full orchestra. And it doesn't even sound like a basic piano. Like my brother, who's 7 years old, can probably play better than that. It doesn't sound human. That's where performance RNN comes in. This is the next level up. So normally what happens is that Mozart, when he wrote his music, he wrote it out in a score. When Magenta is writing out its melodies, it's writing it out in terms of MIDI, which is sort of like the sheet music. So that's what the score is telling. But then the musician's job, the performer's job, is to take that and interpret it, play with it, make it expressive, make it sing. So essentially what the performance RNN is trying to do, it's trying to get rid of that middle step. Instead of the AI generating the score and then trying to perform it, essentially it's generating the expressive performance as it's going. And this is what, like, personally, when I like try and compose something new or try and work out an idea, I don't do it in front of a computer screen. I do it in front of my piano because then I can actually hear, okay, this is how I would play it. This is how I would sound. And that allows me to give it that human touch. So that's what magenta is trying to do. And essentially the way it does that is by increasing events. So the 128 note on and note off events are basically saying, is this note on at this moment or is it off? So that's pretty simple. But the real key is the 100 time shift events. So essentially what this allows to do is it allows the AI to actually skip forward in time in increments of 10 milliseconds all the way up to 1 second. So that's what gives you the 100 time shift events. So what this gives you is essentially like, it gives the AI kind of a license, like, here you go, you are allowed to play with the tempo. You are allowed to play with where the notes are. It doesn't have to stick right to the grid. And velocity, again, is dynamics. So it'll, instead of coding velocity hard-coded, like saying, okay, this note is this volume, this note is that volume, instead it's going to decide as it goes. It's going to decide as it performs. So this dramatically increases the number of events. So it increases like how expressively it can play. And the way it's trained is actually on professional pianists in a classical music competition. So what Yamaha's e-piano competition data set is, it's like a bunch of professional pianists playing these classical pieces for competition, right? So all the note timings and note dynamics and all that is based on the human playing it, not on the computer. And all the pieces were composed and performed on piano, so it gives like a sense of consistency, like the AI knows that this is going to be a piano song. And we also don't even have to do any real curation, because all the pieces were classical repertoire selections, and all the people who are playing are at the highest level of piano performance. So the AI is literally learning from the best. So we don't have to do curation. We don't have to get rid of the low quality stuff. But again, it's not quite there yet. Now we got to use transformers. So RNNs are great. They've been doing a lot of great stuff for a while. But the problem is that it has to sequentially, it's like building the tracks as it goes, right? It's going forward and it's building the track and it's building the track, and it has to build the track it's on right now before the next track and before the next track. So what do you think what do you think that's creating? Like, what problem do you think that's creating? You guys can unmute, shoot your answers.
Short-sightedness.
Sorry?
I said short-sightedness.
Short-sightedness, okay, one. That's one of them, definitely. I'm looking for something else though. All right. So the answer is they're really, really resource greedy. So the short-sightedness is definitely true, and it's one thing that this new model solves, but the main thing it's trying to solve is that RNNs are super resource greedy. It has to compute one step and then another step. And the general trend in computing is always to do as many things as possible at once, right? So we don't want them to have to wait. We don't like waiting for things. So essentially, we take the attention mechanism for an RNN and get rid of the recurrence entirely. So there's this paper called Attention is All You Need. And basically the main structure of this transformer model is a bunch of encoders that it's been used in like natural language processing. So you take a sentence in French and then you encode it a bunch. So now it's just a bunch of numbers. And then you pass that numbers to a stack of decoders, and those decoders decode it, but in English. So you take the French and then you make it into English. Each encoder has this sort of structure. And this self-attention is where that attention mechanism comes in. And then this is your regular standard feed-forward neural network, right? So basically what it allows it to do, it allows it to learn long-term dependencies, like you were saying, so that it's not short-sighted, and it's also computationally much easier to train and much faster. So if we look here, so each of these circles is like showing how it depends on what it did before. And if we skip to the end, you see this kind of quirky motif is coming back. And we can see that it's actually going back all the way here, which a regular RNN would not be able to do. It's going back all the way and it's taking information from those and using it in the moment. And that's what allows it to create these like overarching pieces that actually try and tell a story and not just like a random wandering melody. So it gets rid of that short-sightedness, and it's also much more efficient. So the general idea, I'm gonna speed through this because we don't have a lot of time. And basically you want to encode in words, you want to encode these as like, you want to encode these as numbers. So this is essentially how you would encode it in numbers, blocks, whatever. And then you multiply it by these matrices. So this WK essentially means that, oh, this is what we're training. This is what we're training it to do. And then you multiply X1 by WQ to get Q1. And then same thing for WK, you get K1. And these are just abstract kind of representations, but these are kind of scary, but it gets better. So essentially each of these vectors is used to calculate like an attention score. So essentially the neural network is actually going to score, okay, how important is this piece of information, right? So it's going to take that, it's going to divide, and it's going to do a softmax, which basically makes it add up to 1. And then basically we're going to highlight like, oh, this is important, we're going to highlight it. And this is not important, so we're going to make it way less important. And then we sum it up at the end. So then essentially what it's doing, it's saying, okay, what are all the things I've learned in the past? What are all the things I've done in the past? And which one is the most important that I can actually use now? And then what we do, we basically just do that, but a lot of times. Like we have 8 different heads in the original model. And the idea is that each different head of attention is going to detect something else. And together they're going to detect, we're going to be able to extract meaning. So here we have the animal. This head of attention is strongly biased towards the animal. And this one is biased towards tired. So essentially it's going to have, together they say, oh, the animal is tired. So it's connecting the beginning of the sentence to the end of the sentence. And that's what these transformer models aim to do. And this is a basic transformer, but the last thing we have to do is we have to make it relative. So absolute measurement is like if you literally took a ruler and you measured let's say you want to measure my laptop and it's exactly X amount of inches. But what if you want to know how much longer it is than something else? Absolute measurements can't help you there. So we want to use relative measurements. And relative measurements are what's really important in music. In music, we don't care about the specific frequencies of each note, or we don't care exactly at what time these things occurred. We care about where they are in relation to each other. We want to care that, oh, the distance between these 2 notes is a major third. And that's what makes it, oh, this is going to be a major chord, or this is going to be a minor chord, or this is going to be happy or sad or fast or slow. We care about how they are in relation to each other, not what they actually are. So if we change these attentions from absolute to relative, we get a way better model. So now here's this transformer model conditioned on the chord progression from Hotel California. That's crazy. Like if you told me that an AI composed it like 6 months ago, I would not have believed you. And here's something I did just for fun. I took the lick from earlier and I had it harmonize it. And a lot of people might not pick this up, and I'm a music theory nerd, but basically what it did at the end is it used this harmonic technique called le tierce de Picardie, or Picardy third, where essentially you have like something in a minor key, but you end on a major chord. And that's just so cool to me that it actually like learned this harmonic idea, but it used it to harmonize this melody. Like this is something that not the average musician knows, and it actually picked up on that and used it. But we're not quite there yet. And this development was actually just 2 months ago. The idea is that you give this transformer model a style. and then you have it generate a performance in a similar style. So this makes it like a creative tool. Like you say, oh, I want it to be a little bit jazzy. So you give it a jazz type conditioning, and then it'll generate a jazz piano piece for you. Like, that's crazy. Like, you took a style of music, and somehow from that data structure, you managed to say, oh, this is what makes it jazzy. So now I'm going to take a completely different song. It's different music, but it's going to be in the same style. And that's how we're actually going to get RoboBach. Like, that's so cool to me.
That's amazing. Thank you, Tron.
I don't think the musicians at the Philharmonic are going to be too happy with you, however. But it is amazing.
I feel super dumb right now, super, super dumb. But that was amazing, John. I just have one question. This is really cool. I've never heard about AI in music, but that definitely makes me wonder what more we can do. But the fact that when we define good music, we also say that it's something that generates emotional response.
Yeah.
Say nostalgia, it makes you feel sad or happy. Do you think that can eventually, do you envision that one day we would also be able to merge that with the fact that we can actually create personalized music for individuals based on your emotional need?
Yeah, so in music composition, we often like we learn these type of like idioms or languages. Just how when we speak, we kind of learn that, oh, this type of word elicits this type of emotional response. In the same way, this type of like chord progression, this type of melody, it takes a certain, gets a certain response, or this type of like emotional reaction. So when I compose music, and when I learned how to compose music, I always think of, okay, how am I trying to make them feel? So the idea is that we want to impart that sense of emotion to the AI. So we might train it on a bunch of samples of just happy music, or music that would make someone feel happy. And then based on that, it'll extract some sort of generalization of, okay, these are the characteristics that will make it happy. And we will never know what characteristics it's actually looking for. But as long as it generates that music that makes us happy, then I don't think there's any problem with that.
That's really cool. Thank you.
I think the one thing is that the beauty is in the high eye of the beholder idea, that like everyone reacts to music in different ways, but in the same way that like a jazz musician makes music for a certain type of person, right? A certain type of person who likes jazz. In the same way, we can train multiple models to kind of cast a wide net, like, oh, this is going to be our pop model, and we're going to train it only on pop music. So I think that's where the idea of personalized music is heading.
That's really interesting. Thank you.
Hey, have you ever heard of this being used outside of like Western 12 semitone kind of music into like?
That is interesting. And no, I haven't. Like, most of this is entirely trained on Western music, just because of how like the data structure that we use, like MIDI, is designed for Western music.
Yeah.
So it's something interesting that no one has really explored yet, like different tuning systems, like maybe just intonation, or like different tuning systems from like Eastern music or like Middle Eastern music. Like that sort of thing MIDI doesn't allow for that, but like
yeah.
It's something super interesting that hasn't been explored.
And you could like mesh those together even and try to come up with something.
This is actually like linked off of that. I was thinking, because I watched a video recently of someone who was analyzing flamenco music, and there's like actually specific beat patterns that are used in like every single flamenco song, and they only vary by like certain beat counts, and like how, let's say it's the exact same rhythm, like almost on a clock. If you, let's say you were starting at 2 o'clock instead of 12 o'clock, that's the only change, but everything else is the exact same. So like that kind of structure would be fairly easy to integrate. I think it'd be a really interesting like project if you wanted to add on to it.
I
Yeah.
imagine some of the Eastern music would be more complex and
Yeah.
a little bit more challenging.
I think it's not like, I don't think any style of music is really more complex, but I think it's more that like the established data structures that we have are super like Western centric. Like when I learn music composition, I learn Western classical music composition. And it's not a distinction a lot of people make. Like when people think of music in their heads, the average person usually, especially in North America, they would usually think of Western pop. But the thing is that there are so many other like ethnomusicologists that actually study, okay, these are the different musical structures and here's how they actually work and here's how they're different and here's how we can use them to make our music sound different or music elicit this specific emotional reaction. Super interesting.
Yeah, one thing, like first of all, I'm pretty impressed with the work, the knowledge, and also the passion. I mean, this is absolutely incredible, and it's good to see that, you know, that you're starting at such an early age with so passionate about, you know, getting to the edge of, you know, music and technology and water and physics as well in the case of the water part. It's really impressive. So it feels really good. And somebody was mentioning, I think in the chat, that great that our future is in your hands in general. So one question that I do have in terms of the music piece is, so you're one thing is like you're trying to learn from, let's say in that example, when you have a lot of these piano cases, you're trying to learn from all these interactions, but then then once you play it, or once your neural network starts playing it, it's creating a completely new composition out of it, right? So that's the whole idea. So it's not trying to mimic anything in particular that is in the sample data set.
Yeah, like it's not, and that's one thing that like neural networks have to do. Like they have to make sure that they don't memorize. So there was an architecture where there was like kind of like a bottleneck in the middle between the encoders and decoders. And what was happening is that basically what it was trying to do is memorizing the samples from before, and it was kind of just replaying them and spitting them back out. So to stop that, that's what the transformer model is also like designed to do. It's designed to make sure that it can generalize and not just.
Now that was a bit of my question, is like, once you want to then create a new composition, then you need to use something as a base always, or you need
No,
no?
you can have it generate something entirely on its own. Like this transformer music app, it's essentially like an infinite, I'm not sure if it's infinite or not, but if you go to this website, I can send it in the chat. Basically, it's just entirely computer generated music. So they weren't conditioned on anything. And basically they just hit generate, and then all these different songs came up, right? It essentially created and composed all these different songs, and they just compiled these songs and put them into an app.
Okay, thanks a lot. Thanks for clarifying. Good.
So I have a clarification around that. So it kind of relates to the question I had. So I actually recently watched Caught Up with Westworld, and I was wondering, so it sounds like if you give it the same inputs, right? So the bass music and same style, that it sounds like it will generate multiple pieces and they're all going to be different. And I'm wondering if maybe that variability in output is kind of what we will come to understand in terms of AI having some sort of consciousness, because it's no longer, we cannot determine the output even if we put in the same inputs 100 times.
Yeah, so that's an interesting idea. And the thing is that the problem with consciousness as a concept is that we don't have a good way to prove that anyone is conscious. Like, we don't have a good way to say, I am conscious. Like, the only way I can say I am conscious, there's no way for anyone else to verify that I am conscious. In the same way, we can't verify that a dog is conscious. So we can't actually verify that the AI is conscious either. But I think what's super interesting is that, like, the idea that we don't actually know like all those different neural networks, we don't know what features they're extracting, but we know that they are extracting some features. So what happened in one case is like they were trying to classify different kinds of pictures, and one of the types of pictures was fish, right? But it turns out, and then they showed a picture of a human hand, and it recognized it as a fish because all the pictures in the training data were of people holding the fish. So what it essentially did, it was like, oh, this is what means that there's a fish there. So we don't actually know what features it's extracting until we try everything, right? So that's what's so complex and so amazing about neural networks. Like they're so good at modeling these things, but we don't quite know how, and I don't think we ever will.
Cool, thank you.
Any other questions?
I kind of have one related to what Wilson was asking. It's a slightly long-winded question, but I'll try and condense it.
Okay.
So this whole idea of like consciousness and what it is, from the things I've read about consciousness, it's just a collection of neural networks having at each given moment. So at each given moment, you're essentially a different person whenever those whatever neural networks are active at that point, which is what I think is also being mimicked in this music thing. But when, let's say someone's composing something or they're making music, how is this technology exploring the idea of also there's like intelligence from the neural network, but there's also emotional intelligence, which arguably can be tangible when you start getting into the base level of what an emotion is, when you start transferring it to things like wave patterns and like everything's essentially like a wave pattern. And when you start getting to vibration, so based on how someone's feeling, since that's kind of a tangible thing that you can measure, how are they, I guess, accounting for that in these generations?
So these generations, first of all, these generations, like they don't know who I am. They don't know who you guys are. So they're generating it based on what they've been trained to do. So I don't think AI is really that close to even like being able to emulate emotions or anything. But I think right now, the most of what AI development is doing is like making tools for humans, right? So like this transformer idea, it's creating whole pieces of music, but most of these pieces aren't really that great. Like they're nowhere as near as good as like the greatest human composers or even the average human composers who compose piano music. So the idea is right now, like these are creative tools, right? Like I can, on a random day, I will just go to this website and I'll be like, oh, I want to hear something new. So then I click it and then I hear it and I'm like, oh, I can use this idea in this way. And then that's like a creative kind of outlet. Like you take that and you're like, oh, I can use this, I can play with it. So that's where I think AI music is going right now, like tools for musicians. But eventually I think they'll be able to like model like, this is what this person is feeling right now, so I'm going to generate this kind of music. So eventually the human will be taken out of the loop just by nature of how fast everything is advancing. But I don't think we're there, and I don't think we're close quite yet.
But you know, you said before something that it kind of resonated with me, is that you can play a lot of the musics that people play when they're happy, right? And then your model, like your weights and everything, is being trained around happy music. Somehow the neural network is training or understanding to the certain degree what happiness could be, right? Or it is. So that's a bit like, or at least in music, right? How you express happiness in music through playing a bunch of music that people play when they're happy. Let's say that's an interesting concept for sure.
Yeah, definitely. And I think like it's the human, first the human has to be in the loop. So without a human, how is the AI going to define what makes humans happy without humans. So a human is going to say, okay, this is what makes me happy. This is what doesn't make me happy. And then after that, then the AI will start to generalize and say, okay, this is everything you showed me. So now out of that, I'm going to extract, okay, maybe these are the features that are common to all of them, or are important or not important or whatever.
And you need the music first, right? So the music is generated first by humans.
Yeah.
To use to be trained, and then, yeah. Okay, we can go forever.
Quite at alpha 0 levels, yeah.
Yeah, this is one of those
get
topics.
very philosophical.
Yeah. Yeah, great presentation. Thanks.
I think we are 15 minutes over time, and Michael has dropped off. So I think it warrants a big thank you for you guys for coming in today and speaking to our team. I think everyone found a little bit of value of it, and I hope you guys can follow up with where your projects are. We're so interested and so excited to see you guys grow. So keep in touch, and I think Naveed and Michael will definitely talk more and make sure that you guys are on board and come chat with us more. But I don't want to take any more of your time, and I think most of the team has dropped off. But thank you so much for spending the afternoon with us.
Thank you.
Thanks,
both.
everyone. Thanks,
Thank you,
Naveed.
everyone.
All right.
Thanks, Sophia.
Thank you,
Thanks,
everyone.
John.
See
Keep
you
up
later.
with that passion.
Bye.
Bye.
Bye.